Welcome to the third video on Taylor's series. We're going to go through another example. This will be similar to the previous example, but there were certain things that I glossed over in the previous example. I hope to go over those details in a little bit more carefulness this time, and then the fourth video actually has a fundamentally different example. So I hope that the combination of videos will really help. So we're going to look at cosine of x this time and make a Maclaurin series for cosine of x. Same deal as before, take a bunch of derivatives, plug in the center, which is 0. We're still using 0 for the center because we're talking about a Maclaurin series. And so you have these numbers. We'll copy those again to the next slide here. And then notice that when you have odd derivative numbers of like 1, 3, 5, 7, 9, 11, so on, then c sub I is 0. So the only interesting c sub whatevers happen to be c sub an even number. And here they are, same thing as before. So here's a Taylor series for cosine of x. This is the Maclaurin series for cosine of x more specifically. We'll copy this to the next slide and sort of do the same thing as before. We want to do some pattern recognition, but now we have every even number, right? So every other number again, but now we want to find a nice formula for 0, 2, 4, 6, 8, and so on. And that's very nice to describe because that's just 2 times m, as m runs from 0, 1, 2, 3, and so on. So if you use the formula 2m, plug in m is 0, you get 0, plug in m is 1, you get 2, plug in m is 2, you get 4, and so on. So this power series, this Taylor series, which is a power series, you can do some pattern recognition and summarize like this. Okay, so this one actually looks a bit nicer than the one for sine of x. So let's take this power series and look at the mth term. Look at the m plus first term, and using some algebra this simplifies again, and use the ratio test. The ratio test asks us to look at the limit of the following sequence. And here again you have fixed number over m. As m grows, you have a fixed number over a big number, so the limit of that is 0, and therefore by the ratio test this power series up here converges for all reals, and the interval of convergence is all reals. The radius of convergence is infinity by convention, and so cosine of x will give you the same number when you plug in for x as what if you plug in that same x over here. Doesn't matter what real number you use, these two formulas will give you the same thing. This is a good time to take a break. And coming back, so here is the Taylor series representation for cosine of x. And let's talk about Taylor polynomials again. So here are the terms of this power series written out. This is when m is 0, this is when m is 1, this is when m is 2, and so on. But it will help, again, as before, to write out all the terms, including those with 0 coefficient, so you get something like this. So just to try to drive home the point, C0 is 1, C1 is 0, C2 is negative 1 over 2 factorial, C3 is 0, C4 is 1 over 4 factorial, C5 is 0, C6 is negative 1 over 6 factorial, C7 is 0, C8 is positive 1 over 8 factorial, and so on and so on. And so as before, let's identify the partial sums. Those things happen to be called Taylor polynomials. So here's Taylor polynomial t sub 0. There's t sub 1, t sub 2, t sub 3, t sub 4, t sub 5, t sub 6. This goes on, of course, but before this gets unwieldy, I think we're just going to deal with t sub 6 here. And as before, the remainder is take your original function, f of x, and subtract t sub 6, and that's r sub 6. So think of r sub 6 as being the error between the original function and our approximation. So t sub 6 is nice to deal with because it only has a finite number of terms. This formula, just stopping right here, is something that a computer can understand. Of course, a computer can understand stopping at 100 terms as well. And of course, something more like 100 terms is the point, but we'll do 6 by hand here. And the point is, again, we use m equals 1 as an upper bound for the 7th derivative of cosine of x, and that makes sense because the 7th derivative is going to be either plus or minus sine of x. I don't even want to think about it, but sine of x is between negative 1 and 1, so using m as 1 works. And so what Taylor's inequality says is that the error between cosine of x and this 6th Taylor polynomial, that the error, this absolute value, is never going to be more than 1 over 7 factorial times x to the 7th power, as long as you look at x values which are within a distance of pi away from the center 0. So let's recall some of this information and use this and look at a picture. So here's T6 again, here's R6. The inequality we saw earlier looked like this. What did this mean? Well, to demonstrate this using a different value, we're looking at x is equal to 3 here. So just replace the x's here and here with a 3, and this formula makes sense. This is okay because 3 is smaller than pi. So what does this inequality really mean? Well, r sub 6 of 3, let's plug in a 3 here, says cosine of 3 minus t sub 6 of 3. So we'll compute t sub 6 of 3. That means just plug in a 3 for the x's that are here. And we'll compute cosine of 3, although we won't really compute, but just write that. And then the point of this inequality is that these numbers, these two numbers, so this first number right there, and then, this should say cosine, not sine, that's a typo. But so this number and then cosine of 3 are within this number right here. So I rewrote that right there, of each other. So let's see that in the graph. Here's the graph of cosine of x. Here's the sixth Taylor polynomial, and we're going to look at what happens at the x value 3. So I drew the appropriate point on the graph when x is equal to 3. You actually see the two dots. They overlap in the picture a little bit. Maybe that's an anomaly in the picture, but that's how close these y values are to each other. They're within this number of each other, 3 to the 7th over 7 factorial. So that's how nice Taylor polynomials are, in that they approximate. So this thing, which only has 4 terms, nice algebra thing. You can give this to somebody who's never taken calculus before, and they can understand something about this polynomial. This is pretty darn close to cosine of x. Time for another break. Welcome back. Like before, if you wanted to find a Taylor series for x to the 23rd cosine of x, finding a bunch of derivatives is not the right way to go, because the product rule is going to really mess with this. And so, I mean, just try it. Try writing out the third derivative, and it's just going to be a bit of a mess. So using that general method, or that method 2 as it was called, is nice only when you can find a nice pattern for the derivatives, and this is not the one. So what do we do here? Well, here was that short compact form of the Maclaurin series of cosine of x. You can multiply by x to the 23rd on both sides, and then just by doing some algebra, you can distribute x to the 23rd into these infinitely many terms that you're adding together. So by the distributive law, this x to the 23rd moves in here. And then finally, just using some algebra, you can rewrite this as x to the 2m plus 23. Same sort of thing. We're going to look at integrating. So we could integrate the function cosine of x squared using power series. So how are we going to find this integral? Same deal. We'd like to use a power series representation of cosine of x squared, and taking the function g of x equals cosine of x squared and trying to take all these derivatives is not going to be so nice because of the chain rule. So instead, start with the Maclaurin series for cosine of x and substitute. Every x now becomes an x squared. This x2 also becomes an x squared. So you have x squared still to the 2m. The 2m here matches that 2m. The x became an x squared. You can do some algebra to rewrite this as x to the 4m. And now the point is, instead of integrating this, we're going to integrate this. And this is just a big old polynomial. Think of this as a polynomial degree infinity in a sense. So integrate one term at a time. And to find this integral, now here's what we do. So because of this power series representation of cosine of x squared that we just saw in the previous slide, to integrate this function is the same thing as integrating this power series. So we do that, right? But let's first look at the indefinite integral. I just really want to set up carefully what's going on. So if you look at the indefinite version of this integral, then you need to look at the indefinite version of this integral. I didn't write that out due to lack of space, but I did the integration. And so term by term, keep the sum, keep this coefficient, and then x to the 4m integrates to x to the 4m plus 1 over 4m plus 1, and there's this plus c. You'll see why this is red in just a second, but now you can use the fundamental theorem of calculus 2. Just replace the x with a 9, that's the upper limit. Replace the x, this is the only x that appears, also with a 3 because that's the lower limit. And this is what the fundamental theorem of calculus 2 gives you as this definite integral. So why is this red? I didn't really go over this in the last video, but I wanted to make this very clear and concrete and tie this to something that you've seen. So if the step of using this information to get this looked a little funky, I want to appeal to something that you already know, namely the indefinite integral of 1 over x dx is ln of absolute value of x plus c. I've highlighted in red the same pieces, everything other than the plus c. How do you do a definite integral based on this indefinite integral? Well, fundamental theorem of calculus. You look at the part in red and you plug in for the x, you plug in a 9, that's this number. Then you plug in for the x, you plug in a 3. Right? So this is what you would normally do. Staring at this, you would all produce this using the fundamental theorem of calculus 2. So do the same thing here. All we're doing is taking this indefinite integral rule, that this matches up with that right there. So to do this definite integral, replace the part in red, replace this thing, plop that down right there, but replace the x, we replace the x here with a 9 because of this 9, so same thing. When you copy this over here, just replace the x, there's the only x, replace this with a 9, so this x became this 9 right there because of that 9 right there. Same thing. Then what happened? There's this minus, so this minus is completely analogous to that one. And then there's this ln of 3. Well, where did this come from? This was ln absolute value. Plug in for the x, plug in a 3. Why 3? Because of the 3 right there. Same thing. Take this formula here in red, just like this formula in red. Write that here, except replace the x. Just like you replace the x here with a 3, replace this x with, well, what number you see right there. And that's, again, a 3. Alright, that's the end for this video. There's one more where we're going to go through a function which is not sine of x or cosine of x.